Hello and welcome to a discussion on acid and base titrations. Acid-base titrations is because there's more than one type of titration out there. We can titrate all sorts of things. When doctor gives you a prescription for a medicine you take home and take, it's been scientifically investigated and titrated to put a certain amount of that particular pharmaceutical into your body. It's been titrated to do a certain thing. So you can titrate all sorts of things. The titrant is a solution of known concentration, and we usually put that in the burette. The titrat's added to a solution of unknown concentration, the analyte, until the analyte is just consumed, or to the stoichiometric point. We also call it equivalence. We'll say equivalence probably more than anything else. And this is a typical pH or titration curve. We note that this started as an acid, and so a base must have been dropped in until we reached a basic solution. When we have equal concentrations of acid and base, we have equivalence. In this particular titration must have been a strong acid, strong base, because it's equivalent at pH 7. And that's because at equivalence, you don't have any acid or base present. You have only water and ions. Those ions, in this case, don't appear to be manipulating the pH off of what would be the contribution of water molecules, making a concentration of hydrogen ion 1 times 10 to the negative 7th. So this looks like a strong acid, strong base titration. So we're going to talk about the types of titrations now, from strong acid, strong base, all the way to weak acid, weak base. So a strong titration is a simple reaction. That anionic reaction is here. And keep in mind that any titration or any neutralization process is a reaction because of this formation of new molecules of water. pH is easy to calculate because everything's negative log. There's no Ka's to deal with. And also equivalence gives us a pH of about 7. This is generally what the curve looks like. And we see at the beginning we only have acid present. At equivalence we have water and the ions of a salt. And then once we've gone past equivalence, in this case doing a base into an acid, only a strong base remains. And the general pattern of this is important. Notice how flat this is and how steep the curve is through equivalence, and then how flat it comes back into the basic range. We're going to use this curve in a question we're going to work on now. Nitric acid being titrated with sodium hydroxide. So let's take 12.5 milliliters of 0.2 molar nitric acid and titrate it with 0.1 molar sodium hydroxide. This is going to be in a container, and this is going to be titrated in. So here we go. Let's start off. Before any base is added, we only have our hydrochloric acid and really hydronium and water. And so we just need to do the negative log of our 0.2 molar solution, which is 0.699. It's fine to have pHs this low. In fact, when you calculate the pH of anything with a molarity of greater than 1, it's going to have a negative pH, and that's also okay. So we're going to cast a point down for where that pH lies at 0 base added. Okay, and we're dropping, in this case, a little different from what I spoke about when the titrant and analyte, but in this case we're going to be putting in 0.1 molar sodium hydroxide into our known concentration, known volume acid. So what if we have titrated in approximately 2.5 mils of base? So what we need to do first is let's interact the base with the acid and then see what's left. But to do that, we need to do a little bit of stoichiometry, and it's straightforward stoichiometry. The acid, we have about 0.0025 moles of hydrogen ions. In the base, since we have 2.5 milliliters, note it's 0.0025 liters times the molarity 0.1, and this is how many moles of hydroxide we've used. We'll then do a before change after, and now these can happen in your head once you get comfortable with the idea, to determine the remaining concentration of hydrogen sorry, not concentration, the remaining number of moles of hydrogen ions here. And we also need to convert that back into molarity before we can contribute it to any sort of a hydrogen ion concentration. So there's the number of moles we calculated with the BCA, and our total volume now is 0.125 liters plus 0.0025 liters. That's the new concentration. This is a typo. It should be 0.0125, and so we have a pH of 0.824. No, this is correct. I apologize. Those added together and divided by 0.225 gives you 0.150 molar hydrogen ion concentration and a pH of 0.824. And we need to put the second point there. Now you didn't see much movement there, and that's consistent with the idea that we should see something that goes relatively flat to very steep to flat again. So what if we've added 5 mils of base? What has happened? So then we need to again calculate the number of moles of each. There's our 5 milliliters times the molarity of the base gives us this number of moles of hydroxide. Before change after will let us know exactly the number of moles of hydrogen ions remaining. And then we divide that by the total volume. Now the volume's changed. 0.0125 plus is 0.0050. So it's 0.2 divided by 0.0130. And that gives us 0.114 molar. And the pH has gone up to 0.942. And so there's our third point. The graph isn't perfect, but you can see what's happening. It's going up by a little bit. Now, after 25 mils have been added, this is going to take us to near equivalence, because the 25 milliliters of base times 0.1 molar is going to give us the same number of moles of base compared to the moles of acid. And so, since we now have 0 acid and 0 base, then what's left in our solution but water? But hydrogen ion concentration isn't 0. Pure water has a concentration of 1 times 10 negative 7. Therefore, pH is 7. So we've gone from there to there to there to there. And so we need to imagine a straight line and then a straight up curve and then back. So let's add up to 35 mils of base when we do that. There's our number of moles of each. We've gone down to excess 0.0010 moles of base, and we'll get that through the BCA. And then we'll divide that by the volume of a total solution, which is now up to 0.0475 liters. 12.5 plus 35 gives 47.5, which is this value here in liters. And now we have a molarity of 0.0211 molar hydroxide solution, which is a pOH of 1.677 and a pH of 12.32. So that will plot thusly. And then go one more, go up to 50 mils of base being added. Here are our mole values again, and you can see how you start to see the number of moles remaining. It'll make your before change after happen in your head, hopefully. Realize how many moles of base you have remaining, divided by the total volume. Again, you need to add the volume at each step, convert to liters. So 62.5 mils is there, and our new molarity is 0.04 molar, pH of 12.6. And so this is not by any means a complete titration curve, but it gives the gist of what happened in the titration. So we went through 5 points and saw several positions on the pH curve that we can calculate what's remaining in the solution and therefore the pH. Now let's do a weak acid strong base titration. This is where it gets a little bit more difficult, but you have the skills necessary if you've been keeping track of the videos. So when we act a strong base with a weak acid, we assume that they're going to go to completion and form water and a salt. Before equivalence, the concentration of weak acid remaining and conjugate base formed are determined at halfway to equivalence. pH is equal to pKa. And if you remember, that's because of the relationship between the anion concentration and the intact acid concentration. Halfway to equivalence mean that when these two are equal, we're halfway to equivalence. And the pH is equal to pKa because this expression can be stretched out. Log of 1 gives 0, and therefore pH is equal to pKa. So when we spoke about halfway equivalence earlier on this unit, this is what I was speaking about. So this is the titration curve for a weak acid strong base. We have acetic acid and sodium hydroxide. So here's our acetic acid. And note our pH is higher than it was for a strong acid titration. Note we start off relatively low, but as we add our base in, we see a little bit of a pop up and then it flattens out. This is the formation of your buffer. And this from here to here is called the buffer zone. And that's the point at which we can add or subtract, add acid or add base, and our pH will stay relatively constant. So let's actually define these points. We only have to worry about Ka with this first point where there's only weak acid present. Then when we have a mixture, we'll have to do a little bit of stoic and work with Ka. And then halfway to equivalence, this is a blessing, pH is equal to pKa. That makes it very easy to work with. And a little further in, we have weak acid is greater than the concentration of strong base, but we're beyond half equivalence, so we'll have to do stoic to determine what's left and then work with Ka. Then in equivalence, the strong base and the weak acid result, we're going to have to deal with a basic salt. Okay, the basic salt at equivalence is probably one of our more challenging calculations, but you've already done this, and so we'll do it again. Finally, when your strong base is of greater concentration than your weak acid, we'll simply do stoich and work with the negative log of our strong base concentration. So that's the gist of these calculations, similar to what we did with the strong, but we have a little bit more to think about. The equivalence point for a basic salt is present when a weak acid and strong base are titrated together, and the pH is going to be greater than 7. Okay, and the reason for that is that the conjugate base of your weak acid will produce, when it hydrolyzes water, hydroxide ions. This is just a collection of the titration curves from strong acid all the way to a very, very weak acid, and the appearance in general of what we see as we titrate them with a base, strong base. And this sort of underscores what I was speaking about, the nature of formation of the buffer in this area, and the buffer zone being between here and here for each of these. So in this particular titration, we're going to be 30 mils of 0.1 molar sodium hydroxide is added to 50 mils of 0.1 molar hydrofluoric acid. Now you might say, this is not a titration. No, it's not. We're forming a buffer. We're building a buffer right now. Here's our Ka value for hydrofluoric acid. Let's find the pH of the final solution. So first and foremost, we have to find out how many moles we have of the acid in the base. And there we have it. This is not going to be a perfect buffer. We did not take down exactly half of our acid, and that was purposeful. So let's build the buffer thusly. And then before change after, we're just going to determine the quantities of what remains. Now notice we have both hydrofluoric acid and fluoride ion left as we've let the base and the acid come together. And that was on purpose. We want to have, for a functional buffer, a concentration of both acid and conjugate base to make it work. So when we do that, we can then divide by the total volume and find the molarity of the hydrofluoric acid and the molarity of the, this should be of the fluoride ion, not hydrofluoric acid, pardon me. So we have the molarity of each piece in our buffer system, and we're ready to titrate. So, So to start off, we take 30 mils of sodium hydroxide, add to our 50 ml buffer, determine the pH of the final solution. Oh, we weren't ready to titrate yet. What am I thinking? We have concentrations. Let's go back to the last slide. We have concentrations here, both your acid and your conjugate base. Let's find the pH of the solution. So how do we do that? Well, there's a couple ways. But the first way is we can put our values into our equilibrium system and allow it to come to equilibrium. And we know our Ka, so we can set it up thusly, neglecting our plus x minus x. And then we have a hydrogen ion concentration of 4.8 times 10 negative 4, a pH value of 3.32. So here we go. 50 milliliters of sodium hydroxide added to 50 mils of hydrofluoric acid, determine the pH of the final solution. Okay. If we add 50 mils of base to 50 mils of hydrofluoric acid, what's happened? We have only the fluoride left. And then 50 mils to a 0.1 molar hydrofluoric acid, determine the pH of the final solution. Pardon. Once we reach this point, we have our Kb. We calculated from our system. Our fluoride is now influencing our system alone. And so we have our Kb expression. We neglect our minus x. And we have a hydroxide ion concentration, a POH converted to a pH of 7.92. So when we perfectly neutralize our acid and base with the hydrofluoric acid sodium hydroxide solution, we get a neutral, or not a neutral, we get an equivalence pH of 7.92. Okay. Now, if we've added 60 mils of sodium hydroxide to the 50 mils of hydrofluoric acid, find the pH of the final solution. Here we are finding the number of moles of acid and base. And now we realize our base has overcome our hydrofluoric acid. And then through a before change after, we can determine the concentration of hydroxide ions present in the solution. Now, in this case, you're going to notice you've created a whole lot of fluoride. Should this contribute to the pH of the solution? And the short answer is no. You have a significant concentration of strong base. Because of that, you can ignore the contribution of hydroxide ions from your conjugate base. Focus only on your hydroxide and ignore your conjugate base to determine the pH of the solution. And so there you have your 0.001 moles of hydroxide divided by the total volume of your solution, 0.11 liters, and that gives you the molarity of hydroxide, which if we give the negative log, gives you a pH of 2.04 and a pH of 11.96. So essentially what we've done is we've worked through a weak acid strong base titration through several points. So I'm going to back through these slides real quick and go back through because I was unclear at one point. So we started off by creating the buffer when we added in the sodium hydroxide solution. And you should note that the pH of our initial buffer solution was about 3.32, which is a lot higher than hydrofluoric acid by itself, and that's to be expected. That's the formation of the buffer we should see. So I'm going to draw a rudimentary line showing if we just had hydrofluoric acid between 1 and 2, initially when we start our buffer system, it's going to flatten, and then we would expect it to. Here's equivalence, and if this is about 7 here, we note that our pH at equivalence is above 7. So our pH of our buffer system before we began is 3.32. And as we titrate in 50 mils, we get to equivalence. And at equivalence, we note that we have only the fluoride concentration influencing the hydrogen and hydroxide concentration of the solution. And you see in this slide, with our fluoride ions, we hydrolyze water, and then we calculate the hydroxide ion concentration using the Kb from the Ka, and then we have the pH showing a basic solution of the conjugate base of a weak acid at equivalence. And then finally we calculated the pH after our base has broken through our acid. Okay. The next type of titration is the weak base versus a strong acid. Before equivalence point, a weak base equilibrium exists. Calculate the stoichiometry and then the weak base equilibria. After the equivalence point, an acidic salt is present and the pH will be below 7. So it's the exact opposite of what we just saw. And then after equivalence, only the hydrogen ions will determine the pH of the solution. So this is the similar graphic. We start off with only a weak base, and then we have several points here. Let's go back one point. We have one point where the strong acid is less than the weak base, and so stoic will be done, and then we'll do Kb. At half equivalence, we have POH is equal to PKB. Again, this is in Henderson-Hasselbalch when we have equal concentrations of the conjugate acid and the base. pH is equal to PKB. POH is equal to PKB. And then another point where we have strong acid is less than the weak base. Well, we will use stoichiometry and Kb to find the pH of the system. Then we have equivalence where we have an acidic salt present that will drive pH less than 7. And then finally where our acid overcomes our base. So here we go. Calculate the pH. 100 mils of 0.05 molar ammonia is titrated with 10 mils of 0.1 molar hydrochloric acid, and there's our Kb. So first, again, we don't have a buffer to start. We have a base and an acid, and so we're going to neutralize. And to do that, we calculate moles for each, and then we find out what remains in the solution. We have, to start, we have ammonia, and we have ammonium ion. This is, again, before half equivalence point. And so as this progresses through and we continue to add the acid in, we will reach half equivalence and then equivalence. This is the molarity of our ammonium ion. and there's the molarity of our ammonia. And those two values can be placed into Henderson-Hasselbalch, or you can do an equilibrium expression like you see here. There are our values. We place them into the KB expression, neglect the positive x and minus, or plus x minus x, and find hydroxide ion concentration in POH. pH for this basic solution starting off is about 10. And then if we calculate the pH when 100 mils of 0.050 ammonia is titrated with 50 mils of 0.10 molar hydrochloric acid, let's see what we see. Calculate the number of moles of each. And in this case, we have our acid completely neutralizing our base, leaving us only with our conjugate acid. And remember, when only our conjugate acid remains, that will drive our system to produce hydrogen ions through hydrolysis of water. Here's our concentration of ammonium, which we can then plug into a hydrolysis reaction, where ammonium reacts with water to form ammonia and hydronium. There's our expression. We have our Ka from our Kb calculated to be 5.5610 negative 10. And then we solve for x, neglecting the minus x. And our pH is 5.37, which is consistent with the conjugate acid of a weak base. And then we have our 100 mils of 0.05 molar ammonia being titrated with 60 mils of 0.1 molar hydrochloric acid. And at this point, we see we have more acid than we do weak base. And then that means that our system pH is determined solely by hydrogen ion concentration. And again, you might be tempted to say, well, do we need to add in the hydrogen ion concentration from the ammonium hydrolyzing water? And the answer is no. This hydrogen ion concentration will be significantly greater and therefore make this value insignificant in the sig figs. So here we go with the molarity of hydronium. We negative log that and we get a pH of 2.2. You might ask what a weak base, weak acid curve looks like. For this situation, the equivalence is determined by Ka and Kb for the acid and base. It completely depends on the acid and base properties before we can know what would happen with the exact titration. But generally speaking, whichever one is stronger or has a smaller K value will pull the equivalence pH in that direction. And this is because of the strength of the conjugate acid and conjugate base. Finally, last slide for titrations. Polyprotic acid and polybasic base titrations will feature several equivalence and half equivalence points. So this says midpoint here, but we call it half equivalence. You'll notice this is triprotic, where we see 3 different half equivalence points. Anyway, what you notice in polyprotic titrations is there's more than one equivalence. Recall that each proton is controlled by its own equilibrium, has its own Ka or Kb. In practice, these are very challenging titrations in lab. However, I think we're going to try one this year. And but bottom line is you have to keep in mind that each one of these reactions is its own thing with its own equilibrium. And outside of that, I think you'll be okay. This concludes our video on titrations. We'll see you for acid-base indicators next.